All right. So chapter 4 is about this microcontroller, which is ARM-based microcontroller, yeah, the LPC1768 microcontroller. So we have you have been introduced to the introduction to this microcontroller already. What is the difference between this and the microprocessor that we have learned before? And we have learned the memory map, all right, the memory space from address 0 to address 4 GB here. What you have here, all right, where the memory is divided into many segments, and this segment is dedicated for specific function. All right, and we also have learned how to configure the I/O port, yeah, to be input or output. All right, we have learned that we have 5 port, port 0, port 1, port 2, port 3, and port 4, and each port is divided into 4 bytes, yeah, by 0, by 1, by 2, and by 3. Right, so we have learned this in chapter last week. Okay, all right, this is how to configure the port. Yeah, if we put 0 inside the FIO DIR or the data direction register, this will make our port be an input. All right, input. For example, bit 7, if you put 0 in bit 7, so this bit will be input. All right, 0, this one input also, 0 input, 0 input. And if we put 1 here, this one will be output. Yeah, will be output. Okay, so we also have look at this. This is the pin description for the this LPC. This LPC 1768. All right, where this is the pin name, and this is the, for example, P 2.0 means that this pin is connected to port 2 bit number 0. Okay, port 2 bit number 0, and this is P213, for example. This pin is connected to P2 bit number 13. All right, so we also have learned this assembly language to just to blink the LED. All right, where we need to configure the port, which one is connected to the LED. All right, and this is from the manual. So the address of the port and the data direction register. So we have learned this already. If you have any question regarding this, you can ask. All right. All right, now go to the next one for today, where we will learn the more easier way to program the microcontroller. Last week, to program the microcontroller is not that easy because you need to open the manual to see the address. You need to access the address. Where is the port? Where is the data direction control? Just to configure the microcontroller, or just to tell the microcontroller where is the pin is connected to. But with this embed, so we can eliminate that step. All right, we can skip that step. All right, because the embed is actually the what we call the API. All right, application programming interface, that will be the medium between you and the hardware. All right, just like a library, right, sitting between you and hardware. Okay, so here is the embed, and this is Embed Microcontroller, the one that you have seen this already in the lab last time I showed you, and I think we have used this already, right? let's look at the Embed. So Embed is the open source platform that is designed to help the developer to develop the prototype easier and faster. All right, it's an API or application programming interface sitting between the microcontroller, which is the hardware, and with the user, which is you. So it is a software also, but this software is the medium to communicate with the hardware. Last time we last week we communicate directly with the hardware. That's why you need to access the address of the I/O. All right, and by using the embed, now the difficulty, the hard work of finding the address is now can be skipped. All right, you can use the API to tell the microcontroller where is your input and what kind of your input, whether it is digital or analog. All right, so we will see later in after this. Okay, so to the embed can be accessed through this website, embed.org. So, and of course you need the internet lah. Okay, so let's see how we configure the or tell the microcontroller where is our input, where is our output using the Embed API. Okay, so the first one is what we call the digital out API, digital out. So this digital out is to configure the pin to be a digital output. All right, what is digital output? So digital output, for example, the LED. All right, LED is digital output. All right, when you send 0, it will off the LED. When you send 1, it will on the LED. All right, that is the digital output. Okay, so to write a program to blink the LED, all right, instead of using the without using API is difficult. So let's go back a little bit here. This is the C program. Later on, we will program the microcontroller using C program instead of assembly program. All right, because assembly program is hard, very time consuming to write. Okay, so for fast prototyping and for application, so the best way is to use the high level language. And in our case is the C language lah. All right, so this is how we use C language to program the microcontroller to blink the LED. All right, by without using the Embed API. So here is the main loop, starting from here to here. All right, so you need to define the address of this data direction register and the port. The port. All right, so this is the address of the data direction register. All right, from the manual, and this is the address of the port. Okay, so to set this port to be an output is by putting FF or 1111 into this FIODIR, right? Data direction register, and this register is 8-bit, 8-bit. Last week we have learned this. Go back to this again, FIO2, this is port 0 byte 0 0 0. If this one is port 2 byte 0, port 2 by 0. So we put all 1, 1, 1, 1, 1, 1, 1, 1 here, meaning that all here, all bit at the port will be the output. So in this case, we set all 8 bits in the port to be an output. All right, but we just connect one LED, in this case to our microcontroller. Let's use the I draw this in the whiteboard, easier for you to visualize this. Okay, let me open the whiteboard. We have our microcontroller here. Okay, this one is connected to LED. Okay, so this LED is connected to which pin? Let's go back to the okay, port 2 bit 5, so it's connected to port 2 bit 5. All right, so it is connected to port 2 bit 5. All right, so if it is connected to port 2 bit 5, so the register, the port, so let's draw our port. So this is our port, 8 bit. The port size is 8 bit. Okay, bit number 0, 1, 2, 3, 4, 5, 6, 7. Right? So this port is named FIO2 PIN0, because bit 5 is located in byte 0. So where is bit 5? Here is bit 5. All right. So this one is connected to this LED. Okay. So what we need to do? We need to tell the microcontroller that this one is output. All right. So to tell the microcontroller that this one is output, so we need another register called the FIO2 DIR0. All right. So this register will 0, 1, 2, 3, 4, 5, 6, 7. All right. By putting 1 here, meaning that this one is now output. Okay. This one is now output. All right. But in our program, to make it easy, because this one is unused, right? Bit number 4, 3, 2, 1, 0, 6, and 7 is unused. So to make the our programming easy, so we just put 1, 1, 1 1 1 1 1. That's why we have move FF into this register. All right. So let's look at our program. Yeah. Yeah. All right. So that is why here we put FF into R2 and send that value to here, to the one that pointed by R0, and R0 is this. All right. And in C programming, is this. All right. So this is the same program actually. And the previous one is the assembly using assembly language, and this one using the C language. All right. Here, FIO to DIR0 is equal to FF. Yeah, FF. That is this. All right. So actually, we only want this bit number 5 of this register or this memory address to be 1. But to make our program simple, so we put just make all 1. FF, easier. All right. Now we want to turn on the LED. How to do that? So turn on the LED is by make this bit to 1. All right, this bit to 1. All right. So how to do that? Meaning that we need to assign this this port or address to number. What is this number? Should be this one, should be 0 0 0 0 0 0 0, right? Or all 1 also can, no problem, because this one is not used actually. All right, but this one must be 1. So in this case, for example, we make this one is 0 0 and the others are 0. So this should be number 2 and this should be number 0. That's why we have 2 0 here in our program. All right, 2 0. So this will turn on the LED. All right, because this one is connected to this port 2 bit 5. So this LED will turn on. Okay. Now we call the delay function. So this delay function is actually to reduce this number, this very, very big number, by 1, all right, until 0. So when we go to this delay function, now you can see in real time that this LED is on. If you don't have this, after you on and you immediately off and go back to on, because the microcontroller is running very fast, is connected to a very fast clock. So if you don't have this, then you cannot see the blinking LED. All right, what you can see is the LED is always off. All right. So if you have the delay here, all right, means that you slow down the microcontroller for a while, all right, until this job is finished. So you can see the microcontroller is on here, and when you send 0 to this again, to this pin again, and you can see the LED is turned off, and it will go back again and again and again forever. So this while in bracket 1 and starting here and ending here means that your program will be inside this loop forever. All right, until you switch off the your microcontroller. Okay, so that is how to write in C, and this is without using the API. Means that you need to access the port. You need to access the address. You need to open the manual to look at where is this FIO2 DIR0, This is the address according to the manual, and this is the FIO2 PIN0, and this is the address. All right. So that is the hard way. Okay. Now we will look at the easier way. All right. The easier way using the Embed API. Okay. How to do that? Okay. So go back to this. So by using API, our program become this. All right. Before that, I need feedback from you. Okay. Wait. Any questions so far? All right. I just review what we have done last week. Yeah. So last week we have done this using assembly language, where we need to set the I/O pin by assign the I/O pin to the correct address, and where to find the address by looking at the manual. All right. For example, this one FIO dir0, FIO2 dir0. This is the address 40, and for the port one, this is the address. All right. So this is how to program using assembly language, and today we look at how to program for the same application using C program, C language. All right. So any question? So this is exactly the same program with the one that we have looked at last week. Okay. I hope that is clear before we proceed to Embed API. All right. More feedback? Any question? We will have very interesting programming lesson later on, and we will have simulation. Yeah. So the learning will be a lot more fun. Yeah. Okay. So you can use your own computer to do the programming and to do the simulation. Good question from Siti Mariam. So anyone can answer Siti Mariam question? How do we know that bit 5 is located at byte 0? Good question. How do we know that? We need to go back here. The port. Yeah. This is port, right? So let's look at port 2. So this is port 2. Okay. So this is port 2. Okay. So where is bit number? This is bit number 0, bit number 1, number 2, until bit number 31 here. Now where is our bit 5? Here is bit 5. So bit 5 will be located in byte 0 exactly, because byte 0 is from 0 to 7. The next byte 1, will be from 8 to 15. Byte 2 will be from 16 to 23. And byte 4 will be 24 to 31. So if we are looking at bit 23, for example, so it will be located at byte by what, Siti Mariam? 24. Sorry, 23. By 2. Yes, correct. By 2. So that is how. Yeah. So for example, if we go to this, right? Make it bigger. So for example here, let's look at here. Okay, DIP 20. DIP 20. So this one will be port 1, bit 31. So bit 31 will be byte 3, right? Byte 3. So port 1 byte 3. So to access this must be port 1 byte 3. Okay? Yeah, byte 1. Let's go back to this one. This is port 1 byte 31. So byte 3, yeah? Byte 3. So to access that port, okay, let's go back to let's clear on this. So for example, this one P1 31. All right. So let's go to the whiteboard such that the concept is clearer. Okay. So we have P1.31, right? So this means this is port 1 byte 3, correct? So the port will be FIO 1 PIN 3. Okay, and if we look at what inside, so this should be bit 31, 30, and then this is bit 24, right? Okay, so we are looking at this one. So if you want to send, for example, if you want to set this to 1 and the others is 0, okay, so how to do? So this can be easily done by assign FIO 1 PIN 3 to this should be 8, 0 in hexadecimal, right? So this is how. And if you want to clear, just send 0, 0 to this register. Okay. Any other question? Is it clear? All right. So if you have a final examination question for last year, I think last year. So there is one question asking about this. So you can try to refer to that, how to answer this the question. All right. So in your exam also you should expect this. So last time in the closed book exam, so the manual, all right, part of the manual that you need to use is given. All right. So you need to refer to that manual. All right. And answer the question. But for take-home exam, the manual is not given, so you need to have a copy in your computer. Okay, so all the instruction set is available to you, so it is not given also. So you can open your lecture note, or you can open the books, right? Or you can go to internet, no problem, right? Okay, so let's proceed. Proceed our this to this again. All right. So this is the same program also, all right, but using the embed API. All right, so let's see how to use the embed API. All right, so first thing is you need to include the embed header file here. All right, and here is how to configure the IO. All right, the IO. So in this case, we're using the digital out API. All right. So this is digital out API. So this name LED1 is actually the LED1 in your Embed microcontroller. So let's go back to the Embed microcontroller. Where is it? Here. This is Embed microcontroller. All right. So you have 40 pins here, and you have the ARM Cortex M3 core is this, yeah, the IC here. All right. So this is the ARM Cortex M3, and you have actually pins that connected to the outside here, and also you have the LED here. You have 4 LED. All right, 4 LED for testing. Okay, so this LED, the name of this LED is named LED1, LED2, LED3, LED4, capital letter. So in this case, this LED1 is actually this. Okay, right? So we create the object called my LED. So my LED is your object, so you can name whatever you want. You can name whatever you want. All right. In this case, name my LED. You can name LED1, LED2, but cannot be the same as this one lah, because this one is used by the embed library. All right. It's fixed. All right. This is your object. Your object, so you can use any name you want. But the name cannot have. You cannot put number before the alphabet. Need to have alphabet and number. All right. So in this case, you tell the microcontroller that LED1, you name it my LED, and this is output, digital output. All right, digital output. And in your main loop, while one also means that the program will always loop here. All right. So to make the LED on is easy now. So you just assign 1 to my LED here. So this will turn the LED on already. And this is wait function, the delay function, all right, function in the embed.h, yeah? So you can straight away use it. Wait 0.2 means that you delay for 0.2 second, all right? So the wait function, you can have wait for second, wait ms for millisecond, or wait us for microsecond. All right, you can choose which one you want to use. In this case, we want to wait for 0.2 second. All right, so you on 0.2 second. After that, you off 0.2 second. You go back on and off. All right, so you have blinking LED. All right, much easier as compared to this one, right? Because now by using embed, you skip this one. All right, no need to open the manual now. All right, no need to know where is port 2, where is bit 5. Yeah, the only need to know is your LED want to connect to which pin. LED1. If your LED is from outside, for example, from outside, all right, you connect your LED to P5, for example, to P5. So in your program here, LED1, you just change to P5. then done. All right. And let's go back to the pin description. So here, all right. So you see here P5 until P30. All right. The color is blue here, meaning that this pin can be configured as digital input or output. All right. And this one is special function you can configure as the SPI, where we will learn in chapter 5. Yeah. All right. This one chapter 5, and chapter 4 is only the blue pin. All right. And this one can be configured as analog input as well as this 6 pin. So we will learn after this today also. And PWM in chapter 4 also. And this CAN we not include in this course. Serial communication we will learn. Serial and I2C we will learn in chapter 5. Okay. All right. So now let's write the program in the Embed Compiler. So the Embed Compiler, you need to go to the internet. Yeah. So let's go to the internet. Okay. You need to open your browser. Do you have your computer with you now? You can try your program after this. I will show you first, because this one I show you using the real hardware, yeah, the actual hardware. Later on, we will use the simulation. All right. So let's go to the internet. All right. So you can. Okay. So this is the the compiler interface. So you can go to Google and type Embed Compiler, and of course you need to register, to create an account, in order to use the this online compiler. So I think we have done this in our class before the MCO. So you can go to the compiler. All right. Okay. You can have your new program. All right. And make sure that the platform is using LPC1768. If you use other microcontroller, you can change here, yeah, and just click OK here. Oh, I have this program already, so maybe I can use this one. Okay. So but the program is different, so let's change the program to the one that we have here. Okay. So just, all right, the beauty of programming, you can always copy and paste, right? Yeah. Paste your program here and try to compile, and okay, I have the microcontroller with me, so I will show using the this microcontroller first. Yeah. So to download the program is very easy. Just compile. Okay. And save your program in the here. When you connect your Embed microcontroller to your PC, so you will see the Embed microcontroller just like the another drive of your computer. The name is Embed. So this is the flash memory inside the Embed microcontroller. So you just save inside here, save it. So means that the program is now in the in the microcontroller. And now let's all right, look at the program. So if you can see this, yeah, can you see this? All right, so when I click reset here, the LED should blink. All right, so the LED will blink every 0.2 seconds. All right. Okay, if you use the same program before this, yeah, without using the embed, you can have the same same output as this one. All right, now let's use the simulator, yeah, because of this MCO, you cannot access to the hardware already. All right, but if you want to buy one, the cost is not is about the microcontroller only. Yeah, this microcontroller only will cost you 100, almost 200 ringgit. All right, and the board, the application board that attached to this, with the LCD and other devices here, will cost you another 200 ringgit. All right, so the cost is around 400 plus. All right. But luckily we have the simulator for this. You can go to the to this website. Okay, so let's back to this. So you can go to you can use your computer now to go to Google. You can type Embed simulator, or not compiler now, simulator. Okay, do you have that? So here, simulator.embed.com. Okay, click this, and you will have this. All right, so this is the simulator where you have the microcontroller here. Okay, and this blink this LED already, right? So we can test our program by replacing this program with our program. Right, just copy and paste. LED 1 should be this LED also. Okay, and try to run. Click run. All right, so you can have your, you can test your program here. Okay, now let's say we want to change this by using external LED. So you can add the component here. So see, this is add component. So you can click this, and maybe you have red LED, and we want to connect to, for example, in our case, we want to connect to which one? To here, P5, for example. All right, we want to connect to P5. So how to do that? So let's go back to this, right? P5. So red LED, or you want blue color, yellow color, white color. You have 4 options. Okay, in this case, try to use red, and this is LED, and connect to which pin? So in this case, we want to connect to P5. So add the component here, P5, and in your program, you need to change to here. All right, LED 1, you change to P5. All right, and P is lowercase, not capital case. Okay, so try to run. All right, now our P5 LED is blinking. All right, you can try to do on your own. Anyone with computer now, try to do this. All right, I want you to try to do this first before we proceed to the next one. All right, and give feedback to me. If you want to ask any question, please. Yeah. All right. And for your information, in your examination later, final examination, we will use this one. You need to use this one to answer your question. All right. So try to familiar yourself with the simulator. Okay. So if you manage to do that already, so we will continue with the next one. Okay, good. All right. So here, in this component, you have many component that you can use. You can have this push button switch, analog potentiometer, PWM speaker, the temperature sensor, the LCD display, and even the touch screen. LCD touch screen you can have also. Okay, so now what about input? All right, here is output. Okay, so input, to tell the microcontroller that this pin is connected to input is by using digital in. Just now we used digital out, now we use digital in. Okay, for input, right? Digital in and digital out is for one pin. All right, what if we have multiple pin? All right, for example, we connect to one port. For example, we have 8-bit, right? So for example, we connect to 8 LED and we have multiple input also. So how to do that? All right, so in that case you can use the digital out many times. For example, digital out my LED 1 LED connect to LED 1, digital out my LED 2 connect to LED 2. For example, like this. For example, we have where is it? Okay, for example, we have another LED that connect to blue LED connect to P6, right? Okay, so you can have another digital out. Digital out. Let's say this is my LED 1, or just the second one is LED 1. Connect to P6, right? And here you want to on the, or you want here you want to off the LED, the second LED, the blue LED. So you can copy, right, and make this one. So okay, when this one, the red LED will on, but the blue LED will off. Here also we have 1 equal to 1. Yes. All right, let's see. Run. Something is not right. So if you have the syntax error or error in your program, so it will give you compilation fail, and you need to see what is the error, right? So in this case, it say that this one is wrong. Oh shit, yes, digital spelling, so it should be A, right? And compile again. All right, if no error, so it will run like this. All right, alternate like this. So we can see that when we want to add another input, so you need to have another digital out. if you have another one, digital out. There are many digital out if you have many output, right? So that is not a good way. Yeah? If you have the same type of output but using digital out API, that means you need to have many declaration here. So the best way is to use the bus, the bus function. All right, bus in or bus out. In this case. So yeah, so you can use bus in instead of digital in. Right. So bus in is flexible way to read multiple digital in as one value. Right. Bus out is for digital out. Okay. So let's say we have this application, simple application where we have this flowchart. Remember this flowchart? This is the same flowchart as what we have in chapter 3, programming using assembly language, right? So this is exactly the same flowchart, but last time in chapter 3 we programmed using our assembly language, and now we want to program using C language and using the Embed API, right? So first is we declaration here. We turn off the LED, and if we test the switch here, if switch 1 is turned on, so we will turn on the lower 4 LED. If switch 2 is turned on, so we turn on the upper 4 LED. But if both are pressed, so we turn on all LED and go back. All right. So this is the flowchart. Okay. So now instead of using digital in, you can use the bus in. Bus in. All right. So P16 and P20 is connected to the switch, and we name it switch 1, 2. All right, switch 1 and switch 2. Okay, P19 and P20. Okay, and this is the program. So we use this is our main loop. The while one loop means that our program will continuously loop here, repeated. All right. And we use the case statement here. All right, case statement. So to use case statement, you need to have a switch statement, and what you want to check in this case is switch 1, 2, which is P19 and P20, and this is the case for both are 0, means that not pressed, and the output is 0, 0 means that all are off, right? So actually you can use the if else statement also, but if you use if else statement, the program will be much longer. So if you have many input combination like this, the best way is to use case statement. Yeah, all right. Just like in digital design, where you learn which you learned last semester, right? If you have many input combination, the best way is to use the case statement, right, as compared to if else statement. Okay. So if 0, 1, so the output is F0. Yeah. All right. F0 means that the first 4 is 1, 1, 1, 1, 1. The last 4 is 0, 0, 0, 0, 0. And if 2 or 1, 0, all right, the output will be 0, 0, 0, 0, and 1, 1, 1, 1. So the first 4 will off and the next 4 will on. But if 1, 1 or 3 means that both switches are pressed at the same time, so all are on, all right, FF. And LED out default means that other than this combination, sometimes can happen, right? Other than this communication, because this is hardware, yeah, there is hardware glitch and so on. So other than this combination, we put it to 0, 0 or all off. Okay, now the question is, what is how the connection is? P21 is connected to where in this case? In this case, P22 is connect to which bit? P23 is connect to which bit? So here the arrangement is like this. So we need to go back to this. So we have P. Okay. We have switch. Switch 1, 2. So we have one, 2, P19, P20, right? Okay. So if P19 connected to switch 1 and P20 is connected to switch 2, okay, when we say case 0, 1, for example, case 1 here means 0, 1. All right. 1 here means 0, 1. If we have case 2, this means 1, 0. If we have case 3, this means 1, 1. All right. Now, the question is, this 0 is connected to which pin? All right. So in this case, this 0 is connected to P20. This one is connected to P19. All right. It's opposite. Okay. Can you follow? Right. Now this is for switch. For switch. The LED. Our LED, or the name is LED out. So LED out is bus out, right? Connect to P28, P27, P26, 25, 24, 21, 23, 22, 21, right? So when we say this, this LED out equal to 0, this one easier, F0. All right. When we do this, this means we send this F0. F0 is 1, 1, 1, 1, 0, 0, 0, 0, right? In binary. So this one is actually connected to P21. This one is connected to P22, connected to P23, connected to P24, and so on. until this one is P28. Okay, so it's like reverse connection like this, terbalik, all right, can you follow? Okay, so that is how it is connected. So when you use bus in and bus out, so make sure that you know which one is connected to which one. All right. Okay, so now let's look at the example. So we have this. Now let's have this in the simulator. All right, better to do that in simulator. So let's say we have a new one. Let's close this one. Embed simulator. The only drawback with this simulator is that you cannot save your program. So if you have your program, make sure that you save somewhere else. For example, you use Notepad to save your program, or Microsoft Word, or whatever. But here, your setting here, you cannot save. All right. So you need to do redo whenever you want to simulate again and again, right? That is the drawback lah. Okay. But good enough for test our program. So let's say we have this program. So of course this is in the notes. If I have number here 1, 2, 3, 4, 5, this is line number. This is not part of the program. This is for reference. All right. For example, I want to refer to this line, so I seek line number 6. So easy for reference. Easy to explain to you. All right. Line 9. So this is line 9. All right. So in your program, you need to remove this. Okay, remove this. Okay, remove. Okay. Follow this. Right, we don't have this. And okay, I think let's look at the program. So this we have, or we have another, actually we have another close bracket, curly bracket. Right, so I forgot in the notes, actually you need to put another one curly bracket to close this main loop, right? So so you need the push button P19 and P20, so you can do this together if you have the computer. So you can select the push button, all right, connected to P19. Connected to P19, so this should be P19. Add. So this is the push button where you can push later on, and you can have another one is push button also connected to P20. All right, P20 here, and you have 8 LED. So let's use red LED for the first one. Let's say we start from 21. So P21. Add. Another one is P22. P22. Add. The one is P23. Add. P24. Okay, for red, and another 4 is maybe blue. Right. Add P25. Maybe we use blue. For P25. Add P26. Add P27. Add, and P28, the last one. Add. All right, so we have 4 LEDs. So when we press this, this part should on, right? Or which one? Let's see. Okay. So this is P20, so it should be this one. Okay. All right. Any one of you, are you doing the same thing here? Are you trying on your own computer? Okay, good. So I have an interesting issue with the Embed simulator, where when you try to run the program, you can see it's stuck. Yeah, it's stuck. It asks you to wait or exit page like this, and if you press wait and it's not responding, so this is an issue, but can be solved. Can be solved. I forgot to tell you. All right. So do you have the same problem? All right. I wait for you to have the same problem. All right. When you have this same problem, it means that you learn something. Okay. This is a good learning experience, actually. If you experience this and you find a way to solve this, and this will be a good practice. Yeah. And any of you have the same problem, or you don't have? All right. It surprised me if you don't have. Okay. Wait. Yeah. Siti Mariam said wait. Wait with haha. All right. So wait. So actually, wait here. You will wait forever. Actually. All right. This doesn't work. Actually, this program is fine. If you run in the real hardware, it's okay. But for simulation, because simulation is just a software, actually. All right, software that is written to simulate the real hardware, and of course, it's got bugs anywhere. All right, so sometimes it's got an issue like this, but actually there is a solution. Solution. So let's go back, reload the program. I have the program copy here, and go back to the simulator and try to paste again. So the solution is actually to have wait. Okay, so this is the solution. All right. So you need to have wait 0.1 second before you go to test again, right? So this is the while one loop, the endless loop, and before you go to test the switch, you have the wait 0.1 second here before you test, right? That is the solution. So let's say now we have the push button again. So this is the drawback of the this simulator lah. So you need to have this again. So we have what P19, right? Push button add. You have P20, another push button add. You have red LED for P21. P21 add. Is it on? Yeah. Okay. you have P22, and you have P23, and you have P24, and for next one we use blue LED, P25, P26, P27, and last one is P28. Right? So when we press this, yeah, 0, 1 here, means that P19, P19. So the P 21 to P24, P21 to P24 will turn on. When we press P20, this one, yeah, okay, all right, P20, 2 is 10, remember, 10, 10, all right. So this part 25 to 28 will turn on. All right. Okay, can you follow? Okay, good. So remember, yeah, if in your simulation, simulation, most of the time when you want to test your switch, put a delay for about 0.1 second. Cannot be too fast. If 0.005 before this still can be used, cannot be used. So 0.1 is okay. Okay, wait 0.1 before you test the switch, and it will solve the problem. All right, just for simulation. For the actual hardware, it's fine, it's good. No need to have this. Okay, so let's go back to the theory a little bit before we go to the analog input later. All right. So so this is the logic level or voltage level in for the Embed microcontroller. Okay. So for the Embed microcontroller, the 0 volt, the reference is 0 volt, and the maximum voltage is 3.3 volt. So for logic 0, any voltage between 0 and 1 volt is considered logic 0. And voltage between 2.3 to 3.3 is considered logic 1. Consider logic 1. Anything between 1.0 to 2.3 is undefined logic level. So if your input, for example, if you use digital input, if the voltage, the input you give between this is the microcontroller can identify that as 0, and anything between this, it can still identify that as logic 1. But anything between 1 and 2.3, the microcontroller cannot define what logic is that, whether 0 or 1, right? So you need to be careful. Okay. So this is the okay, I explained already. I open, you can have from 5 to 30. All right, digital I/O can be used. And how to connect to the LED to the Embed microcontroller. So the one that we have seen previously is a connection like this. This we call current to LED load. Means that we connect. This is the microcontroller pin. This is the buffer. The buffer represent the microcontroller pin. All right. So you send the voltage to the LED, and the cathode here is connected to the ground. So means that when you send logic 1, so it will turn on the LED. All right, so this is the connection that normally we use, and of course you need to have a resistor here to limit the current, because some LED cannot pass high current, so you need to limit the current by using the resistor. This is another connection that you can use. This we call gate output syncing. Means that you connect logic 1 or 3.3 volt logic high to the anode, and the cathode is connected to the pin, the microcontroller pin. In this way, when you send 0 to the pin, this will turn on the LED, because this is logic high and this is 0, so the current will flow from here to here, so it will on the LED. When you send 1, it will off the LED, because the potential, the voltage is the same, meaning that no current is flowing. All right, so but normally we use this kind of this style of connection, safer, because the current is from the microcontroller to the ground. This one is from the power to the microcontroller, right? This is another example, so you can test this using the Embed simulator. This is blinking using red LED, green LED. I think just like the one that I give you, the example, the second example actually. All right. Example number, this one. This one actually you need the actual hardware, but I show you using my hardware here. All right. Using any digital output pin, write a program which output a square wave by switching the output repeatedly between logic 1 and 0, and use wait function to give a frequency of 100 hertz. 100 hertz means that the period is 1 millisecond. All right. View the output on an oscilloscope. You don't have, right? If you in the lab, then you have. But in this case, I have the oscilloscope here, so I show you later. Measure the voltage value for logic 0 and logic 1. How do they relate to voltage level on page 30? Does the square wave frequency agree with your program value? So we try to write the program for this and check the output on the oscilloscope screen. Okay, so how to write this program? Can you write this program? Of course, yes, right? Easy only. So you can go to the embed here, because we want to use the actual hardware, actual microcontroller here. So you need to use the compiler, yeah. So let's use this program. All right, and before that, so go back to the question. Where is it? You want to output what? Output square wave, right? So the square wave is like this. All right. In microcontroller, the easiest signal to generate is the square wave. Okay, so the square wave is like this. So we want the period or the frequency to be what here? 100 hertz. 100 hertz, meaning that the period is 10 millisecond. All right. So to get 10 millisecond, this means we need to off. All right, send 0 to the pin. 0, logic 0 for 5 millisecond, and logic 1 for 5 millisecond, right? Correct? So go back to the program. So here, This one is actually will generate the square wave already, yeah, because 1 0 1 0 this is square wave already, but this square wave the frequency is quite slow, right? Because this is 0.1, the period is 0.4, the period is 0.4 second. Okay, so we change this to we can use millisecond with ms 5, change to 5 millisecond. This is how we use the width in millisecond. All right, 5 here, and you have yeah 1 0 1 0 for every 5 millisecond, and now you can create the square wave already. Okay, so let's see, this is to P5, and now I connect to my computer to the microcontroller. Okay, so let's all right, let's stop presenting here. Okay, so if you can see this, all right, so this is a microcontroller connected to, this is microcontroller connected to my computer, and this is actually the oscilloscope, the electronic oscilloscope that is connected to the computer, where you can see the output on the computer screen. Okay, so let's launch the software for this oscilloscope. So I have this. Oh, I need to power on the oscilloscope. I haven't powered it on. Right. Go on. Okay. All right, so let's look at the oscilloscope. Okay, so this is the interface of this oscilloscope. Yeah, the scope, and I need to program the microcontroller first, right? I need to compile this and save in the microcontroller. All right, I programmed already. You cannot see, right? Now I connect this to the oscilloscope, to my oscilloscope here, and let's see what happened. Okay. So this is the real-time signal, right? The square wave that is generated by our program. So we can measure the voltage from the high to the low, where this is about yes, this is about 3.3 volt exactly. All right, so logic 1 is 3.3 volt. So we answer the question by observing the logic voltage level, and also the period. So you see the period here. Can you see C1 here? All right, period is 10.01 millisecond, about 10 millisecond. Right, width is 5 millisecond. Can you see that? Right, the period 10 millisecond, and the width is 5 millisecond. So that's exactly what we have done in our program. Okay, any question? So if you can access to the lab, maybe next semester, next year, I don't know, when you do your final year project, right? So you play with hardware. So if you write the program and your program doesn't give you the correct output as expected or according to the specification, so you need to check the signal whether it is correct or not. So how to look at the signal, how to know, how to see the signal? So you need the oscilloscope. All right, so you need to go to the lab and connect your microcontroller to microscope, not microscope, sorry, oscilloscope, and you can see the output. All right, so that is the way. Okay, but in this case we don't have, so I just show you how this is done. And because we now use the embed simulator, so we don't have now. Okay, so now let's proceed to the next. All right, so that will be the digital I/O. Now we will go to the analog I/O. All right, how we read the analog input. All right, because in real life, in practice, you will use the analog sensor a lot. All right, because analog sensor is cheaper, is low cost as compared to digital sensor. All right. So when you want to read analog input, analog voltage, and our microcontroller is digital device. Okay, so you need to convert that digital analog value to digital value in order for microcontroller to be able to process the data from the sensor. Okay, so now let's go back to our slide. All right, we will look at digital to analog to digital conversion. I think for today. Okay, this should be the last part for today lah. Okay. So the analog to digital conversion. So as I said, most of the quantity around us outside the microcontroller is analog. For example, the temperature is analog. All right. The humidity is analog. The light you see around you is analog. All right. So when you want to design or want to have the system that is read that analog quantity and processed by your microcontroller, so you need to convert that analog value into a digital representation before your microcontroller can process it, right? So you need another circuit which is actually embedded inside the most of the microcontroller that we have today, including our LPC1768, right? The built-in ADC, the analog to digital converter. All right, so that device, that circuit will convert the analog value and give you the digital value. All right, so we will learn how this circuit works and how to use that and how to program the microcontroller for that. Okay, so this is example of ADC in microcontroller. So most of the microcontroller only has one ADC. What is mean by one ADC? One ADC means that at one time only one analog signal can be read by the microcontroller. What if you have two? What if you have three? Because normally your microcontroller will connect to many sensor, right? So how to connect many analog input to one microcontroller where that microcontroller has only one ADC. Okay, why don't the microcontroller manufacturer build the microcontroller with many ADC? The answer is cost. All right, you can have many ADC inside microcontroller, but that is costly. Okay, and make your microcontroller circuit big, right? So the best way is to use multiplexer, just like this. So we learned multiplexer already in digital design last semester. So for example, we have 4 input here. So for example, if we want to read this, so we just connect this, set the multiplexer, this multiplexer to read this and send to the microcontroller, the ADC of the microcontroller, and process and give you the digital output. All right. And if we want to read from this analog sensor, for example, so set the multiplexer to read this and this and this. So because the microcontroller is very fast, so it can do this change from this to this to this to this, or even many more very fast. All right. So in our microcontroller, in our case LPC1768, we have 6 input for analog for one ADC. So it is a built-in multiplexer inside there actually. All right, to read from 6 analog input. Okay. Now let's go to the theory a little bit about the ADC. Now the next question is how the digital value is produced from the analog value. All right. How, or in other words, how the digital or how the analog value is represented in digital in microcontroller. So this is the formula. All right. D is the digital value that we want. All right. The one that microcontroller will use to process. Vi is the analog input. V is voltage, analog voltage input. And VR is the reference voltage. So for ADC, always need a reference. All right. So this is reference voltage. So reference voltage can be any voltage depend on setting and depend on microcontroller. All right, and multiply by 2 power of n. So what is 2 power of n? So 2 power of n is the size of the ADC. Okay. All right. So for example, the ADC is 8-bit. All right. So n equal to 8. All right. N will equal to 8. 2 power of 8 is 256. Means that the number that you can represent for digital value is 256 value from 00, from number 0 to number 256 in digital. Right? Again, I repeat. If your if your ADC is 8-bit, so the digital number that you can represent for any analog value is 256 number. All right. So for example, let's go to the whiteboard again. Let's clear this all. Okay. So for example, your ADC is 8-bit. ADC. This means you can represent your digital value from 0, okay, or 0, 8-bit, 1, 2, 3, 4, 5, 6, 7, 8, 8-bit to maximum is 1, 1, 1, 1, 1, 1, 1, 1. All right. So from 0 to 1, 1, 1, 1, 1, 1, 1, 1 is 2, 5, 6. All right. So you have 0, 0, 0, 0, 0, 0, 0, 1, 1, 0 until you have all 1, 2, 5, 6 numbers, data numbers. All right. So that is 8-bit. What if your ADC is 10-bit? All right. Means that you can have from 0, 0, 0, 0, 0, 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. So this, how many is that? How many numbers? Anyone? Very easy. So if we have 10-bit ADC, so we will start with 0 also, and the end will be 2 power of 10, which is equal to 1, 0, 2, 4. So we will have 1, 0, 2, 4 digital numbers that can be represented in the digital. All right. So now let's go back to 8-bit because 8-bit is smaller and easy to demonstrate. Yeah. So now this definitely, if our reference voltage is 5 volt, for example, VR, V reference is 5 volt. Okay, means that the maximum voltage, our maximum voltage is 5 volt, and our minimum voltage is 0 volt. Okay, so all 8-bit will represent 0 volt, and of course, all 1 will represent 5 volt. Correct? Now the question is 0, 0, 0, 0, 0, 0, 0, 1 represent what value in analog? 1, 2, 1, 2, 1, 0 represent what value? 1, 1 represent what value? Okay, so to do that, okay, to do that, we need to use this formula. Go back to this. So what is the formula? This is the formula. D equal to Vi over VR multiplied by 2 power of n, right? So let's do this together. D equal to V input over the V reference or VR multiply with 2 power of n. So in this case, we know D already, right? Digital input is 1. So we want to find VI, analog voltage. This digital voltage represent what analog voltage, right? So we rearrange this formula. Now we want to find VI, right? Analog value. VI should be equal to V multiplied by V. So it should be D multiplied by VR over 2 power of n, right? So it should be, so D equal to 1, right? Because this 1, D equal to 1. So 1 VR, let's, for example, our VR is 5, right? We have R, yes, VR is 5. So 5 over 2, 5, 6. What do you have? Let's use your calculator. Calculator, where is it? 5 5 divided by 256. So you have 0.0195. This is approximately 0.02, right? Yes, correct, Harry. 0.02, meaning that one in digital is 0.02 volt. What about 2? So you can use this formula also to get your result, and it's actually 0.04. All right. So 3 is 0.06 and so on, because the difference between one value, 1 to 2, 2 to 3 is 0.02. All right. So 0.2 to the next is 0.4, to the next is 0.6 lah. Okay. So this we call the resolution of your the ADC. All right. This is the resolution of your ADC. So if your ADC is 8-bit and the reference voltage is 5 volt, so this is the value for each digital analog. This is the analog equivalent value for each digital value. All right. But what if you have this is a question, yeah? What if your input is 0.01 volt? Again, 0 in digital represents 0 volt in analog. 1 in digital represents 0.02 volt in analog. 1, 0 or 2 in digital represent 0.04 in analog, and so on. But what now if we have analog value? Because analog value can be any value, right? 0.01 volt means that something between 0 and 0.02. The answer is we don't have. So that is the limitation of digital. All right, digital is discrete. We don't have any every value to represent the analog value. All right, but 0.02 is I mean the resolution is good enough. Yeah, good enough. We will see this. We call this quantization error. Yeah, we will see this later a little bit after this. Yeah. Okay, but now you need to clear on that. This is digital value, this is analog value. And how we convert, this is the formula. All right. Now let's go back to the slide and let's do this calculation. For example, yeah, if our ADC is 8-bit size, the reference voltage is given by 3.3 volt. So in my previous example, the reference voltage is 5 volt. All right. Now let's change to 3.3 volt. Okay. And try to calculate the digital representation of 2 volt. Okay. So you can use the your calculator to calculate that. All right. So you have your calculator. Of course, you need to change to scientific mode. Okay. Right. So you have 8-bit. So your VI is 2. In this case, your VI is 2 volt. So 2 divided by VR is 3.3. So you have this and multiply by the size of your ADC. So 256, right? Is it multiplied already? No. Multiply by 256. So you have 155.15. All right. So we take 155 because in the data value we don't have 155.15. So we take 155. So let's change to binary. So 155. So we have 1001111. Okay, so that's why we have this 1001111. And if our microcontroller is a 10-bit, so this is the value. All right. Okay, so let's go fast a little bit more. So let's say our ADC is very small, 3-bit. So if our ADC is 3-bit, means that 000 is 0, represents 0 volt, right? And 111 will represent the maximum value, the VR, reference voltage. So we will only have 8 value, digital value, right? If 3-bit, 2 power of 3 is 8. Okay, 0 to 111. So we will see that this is VR. So if VR equal to 1, if VR equal to 1, so we have represented here 1. If VR equal to, change this. If VR equal to 2 here, so we have this. This we have this. This we have this. But something in between, for example, this. Because this is analog value. So analog value can be anything here. So for example, if we have analog value here, so our ADC cannot convert that for us. That we call quantization error. All right. So actually, the ADC nowadays is been give you the nearest value. In this case, is this lah 001. All right. So another terms that you need to know is what we call quantization error. So this is quantization error, and one more thing is we call greatest greatest quantization error. So what is greatest quantization error? Greatest quantization error is this, half of this, the maximum error that you can have. All right. So in this case, half of this is this lah. If this is one, greatest quantization error is 0.5. 0.5. If in our example last time, just now, here, all right, here the greatest quantization error is 0.2 divided by 2, which is 0.1. So this is the greatest quantization error. All right. Any question for that? If no, I will demonstrate. I will show you how to use the Embed Microcontroller to read the analog input. Any question on this concept? I think this part you can read on your own. Same thing actually with other examples. All right. But before that, the LPC, our microcontroller, the size of our ADC is 12-bit, which is very good. All right. So if the ADC is the resolution, the size is big. All right, means that the resolution is higher, and higher resolution, the higher the resolution, the better is the ADC. Means that more and more analog value that we can represent in digital. All right. So this one maybe we come back later. I want to show you the how the microcontroller, especially the Embed, read the analog input. So here again, this is your microcontroller. This is your microcontroller. So you can have analog input here. So you see this pin number 15 to pin 20. All right. Besides, this pin can be used for digital I/O. You can use this pin for analog I/O as well. All right. So P15 to P20 can be configured as analog in. What if you want to use P5 for analog input? The answer is cannot. All right. So if you have analog sensor want to connect to your microcontroller, you need to use this pin only, P15 to P20. Okay. So how to configure? So this is the function, the API that you will use. Analog in. So previously for digital is digital in. All right, easy. Okay. So let's look at the very simple analog sensor that you can buy, and very low cost one, very cheap. You can buy from electronic store. Okay, the LM35. So this is the LM35, the IC, the IC temperature, analog temperature sensor. Okay, so this is the reference voltage, 4 volt to 20 volt. So you can select actually, and the output is 10 millivolt per degree Celsius. This is the sensitivity. Means that any 10 millivolt represent 1 degree Celsius. So for example, 0 volt is equivalent to 0 degree Celsius. 10 millivolt is equivalent to 1 degree Celsius. All right. Okay. So let's say we have a very simple application like this. Our Embed microcontroller is connected to LM35 through P19. All right. And we have 3 LED just like this. All right. So if temperature is too cold, this LED will turn on. If the temperature is too hot, this temperature will be turned on. And if the temperature is between the range, this LED will turn on. So the range is this. If the temperature is exceeding 35 degrees Celsius, this is considered hot. And if the temperature is below 20 degrees Celsius, this is considered cold. Anything between 20 and 35 is considered okay. All right. So very simple application. Now let's look at the flowchart, and remember, before you start writing your program, please have your flowchart. Draw your flowchart first, plan your program. So this is the flowchart for this application. So you can start here, you initialize. So tell the microcontroller everything, where is your input, where is your output. All right. So in this case, you have 1 input, analog input, and 3 digital output, right? So this LED are digital output. And you test the temperature here. So is it less than 20 degrees Celsius? If yes, so we turn on the cold LED and go back test. All right, but if not less than 20 degree, it can be more than 35, or can be something between 20 and 35. So if, for example, it is more than 20 and more than 35, mean that it is hot. So it will turn on the hot LED and go back. But if it is not, means that the value, the temperature that we have read is something between 20 and 35, and this should be okay. All right. So our flowchart is good. Now, how to write the program? So So we need to understand this first, how the LM35 is operated, the operating of the LM35. So each 1 millivolt represent 1 degree Celsius. Therefore, 20 degrees Celsius and 35 degrees Celsius are equivalent to 0.2 volt and 0.35 volt respectively. All right. So this is the voltage that we want to look at. Yeah, we want to look at. In your notes, please change this. This is P20, but in this is P20, P19. So change to P19. Right? Error here. Right? So this is P19. Yeah. And the analog in function, we need to understand the analog in function as well. So this analog in function is any value that is assigned to this analog in is range between 0 and 1. All right, it's normalized to 0 and 1. And our microcontroller, the range is from 0 to 3.3. All right, means that 0, when we read 0 from analog in, when we receive value 0, means that represents 0 volt. And when we get 1, receive 1, that will represent 3.3 volt. All right, that is the function of analog in. Okay, so anything that we get from analog in, we read from analog in, we need to multiply by 3.3 to get the actual voltage value, because value in analog in is normalized to 0 to 1. All right, 0 represents 0 volt, 1 represents 3.3 volt. All right, so to get the actual value, we need to multiply with 3.3, right? So this is the program. Okay, this is the program. All right, so here P20, it changed to P19. Change to P19. So analog in, the name is POT1, POT1 port 1, P19 in this case, because this is P19, so we follow this P19. Digital out for OK LED is P23, for hot LED is P22, for cold LED is P21. All right, and we have one variable here named voltage, voltage. All right, so when we start the program, we turn off all the LED according to our flowchart here, and this is the endless loop, the endless loop. So how to read the value using analog in? So this is how you need to read a value to a variable. So this variable is declared as double or float. You can use float. All right, so voltage is equal to, this is how to read POT1. Here POT1, if you name this as AN, for example, analog AN, so you need to use AN here. This one, because I name it this with POT1, so you need to use POT1 dot read, and you need to multiply by 3.3 because of this. All right, because the value that you get assigned to voltage is normalized to between 0 and 1. So to get the actual value, you need to multiply with 3.3 always. Yeah, always. Now the value that you read is, yes, the actual voltage. All right. So printf, yeah, just skip this. This one we will learn later. And if voltage more than 0.35 means that this is cold, right? According to our flowchart, 0.35 equivalent to 35 degrees Celsius. Remember this 0.35. So if the voltage is more than this, so we need to turn the hot LED hot equal to 1 and cold and OK equal to 0. But if not, if the voltage is less than 0.2, means that less than 20 degrees Celsius, means that the cold LED will turn on. And if not, means that this is okay. All right, and go back, wait, go back, repeat. All right, so let's do this together. So we copy this program to the Embed simulator, and let's run the simulator. All right, so let's copy this. Just copy and paste. Copy. So we go to the simulator. All right, we have this new one. We have this whole program. All right, try to compile this first. Let's see it's okay or not. It's work or not before we add the component. Looks good. All right, looks good. Means that it's run. Now we need the LED, right? The LED, the OK is connected to P23. So in this case, it's P19, right? P19. Change to P19. So you will have the red LED connect to the OK. Let's use white for OK. P23. Add the component. This is OK. What about hot? Hot red for hot. P22. Okay. And we have cold P21. P21. Let's use blue. Cold. So P21. Yeah. P21. Add. Yes. And now the temperature sensor LM35. If you search here, you don't have LM35. All right. You have this SHT31. This is temperature sensor also, but this is the digital temperature sensor, digital sensor. So we will learn this later. All right. Because we don't have that, you can replace that to analog potentiometer. All right. We can use analog potentiometer because this one can give you analog voltage as well. So you can use this, and this is connected to P19. So P19, and of course, when you change this, you need to rerun this, right? And let's see. So the printf here actually is to print to see the output here. We will learn this later, maybe next week. So let's change the voltage. Now the voltage is 0 volt. All right, that's why all are the blue LED is turned on already actually because 0 volt. And when we increase to now I guess something between 0.2 to 0.35. Yes, because see the voltage here is, we print the voltage here 0.255. This is okay, right? So the OK LED will turn on, and we increase the voltage, which is hot now, and the temperature must be more than 35 degrees Celsius, and it is 60 degrees Celsius already, 61. So this will turn on. Okay, and you adjust back. Okay, lower the temperature. The blue temperature, this is okay. All right, so you can have a try here using the simulator, which is fun. Actually, you can learn write your program and test your program using the simulator without the real hardware. All right, try to practice this, and if you have anything or any question want to ask, then you can text me, yeah. And need to do again, and okay, to rush us, need to do again and can understand, or do again means that you do on your own, yeah. You can copy the program and do this, and I will post the video on YouTube so that you can refer back. And oh, one more thing actually, the best way to use the to read the analog value is to have the wait function here, 0.1 second. All right, because sometimes this simulator is not working also, it will start just like we have before. All right, so put the wait function here for 0.1 second, so it will solve that problem. Okay, and in practice also, in hardware, normally for ADC, we have this wait function also, because the although the microcontroller is fast, but the process of converting from digital to from analog to digital value takes time. So it been slower as compared to microcontroller itself. So before you can read, before you want to use the converted value, so better you wait first, you wait first, right? Okay, so if no question, so maybe we can stop our class here. All right, so thank you, see you next week.